Okay, thank you. Thank you for the nice introduction and very much for inviting me to be here. As I said, I really was looking forward to visit you personally, but it is what it is. Okay, so yes, well, you already introduced my background. So I'm originally from Mexico. I'm got a master in computer science there. And my research is in the explanation-based learning and basically for human level AI. This is my contact information, and feel free to contact me if something is not clear or you want to discuss something more detailed. Okay, so first I will give you some examples of the motivation of what we're doing, and this is a digitalization workshop, right? So one of the digital assistant things is the virtual reality. I'm pretty sure most of you have played with virtual reality system that you can see in this picture, in this video here. The digital person is actually just interacting in the virtual environment and just doing dishes, right? But what's the dream? What do we want from this training and from these demonstrations? Basically, this is what we want, right? So we want that the system somehow learns what the human is demonstrating, and this is being transferred to a robot so that the robot later on can execute the same steps, the same procedures that the human just executes, right? And you see in these yellow letters here next to the end effector of the robot, this is the activities or the actions that the robot is also recognizing when he's doing when the robot is doing it itself, right? So this is basically the dream, right? And robotics, we have two main problems. So I'm seeing this as two main problems. So we need to understand human movements, of course. And as you see in this picture here, we have two robots. So we have the PR2 and then we have the iCub. These two robots are looking at exactly the same person making pancakes, right? So you wake up in the morning and then somebody is doing pancakes and you immediately recognize what this person is doing, right? But for robots, it's not that straightforward. So from my point of view, I think that the recognition of actions needs to be robot agnostic and needs to be sensor agnostic. So in this case, it doesn't depend on what robot is observing the same video. They should represent the actions in a similar way, in a semantic representation, an abstraction layer. So from the demonstrations, we can typically observe trajectories like we can have in the picture here. I hope you can see my mouse. And then from these trajectories, what we want is we want to abstract and we want to obtain semantic representation. So the steps that people is doing in order to achieve a common goal. And most importantly, these steps needs to be human readable. So later on, if something fails, the robot is able to explain what happened, why it's not possible to execute this task, or what an error occurred, for example. So then we can have this kind of task representation, graph representation. And then on the other hand, we have the second problem, which is the execution of the action the robot just observed and interpret into the kinematic of the robot. And of course, for this, that depends on the kinematic structure of the robot. And the models needs to be adapted to this new kinematic, to the new sensors, to everything else. And this is a bit more different complexity of the problem, right? So in this talk, I will more focus on the recognition of human movements, how the robots need to abstract these representations. And I will touch a little bit on some of the concepts I'm currently working on to execute those on the robot. And the main problem when we observe humans is that we demonstrate the same action in so many different ways. For example, think of this example of just cutting the bread. How many different ways do you think there is to just cutting a bread, right? So we made an analysis and we discovered that different people have different ways of executing the same task. You see here, this person is basically doing as we were expecting, is just cutting the bread, right? But the person in the middle here, and she's rolling the bread for whatever reason, right? You can see it. And the last person here, the green guy, is left-handed. And then this, interesting, because which one of these demonstrations should we use to train a system so that generally can extract and interpret that all these represent the same demonstration of cutting the bread, right? And this is important because exceptions occur everywhere, and we need to tell the system when something is different and when something is the same, right? And then the second problem, which is the execution. And as I mentioned before, we are dealing with different robots, and different robots will have different sensors. Like in this case, we have the PR2 and the iCub. One is a dual arm, one has one arm, one doesn't move. But then we have another robot that is mobile, but is also with a tactile sensors. And then we have the bipedal walking robots, right? Like the humanoid robots. And we have all the different sensors like RGBD data, force sensor, lasers, tactile information, etc. This is just some examples. This is information about the robot. Now imagine you have the information that you can obtain from the room. So now you have virtual realities, you have motion capture system, external cameras, etc. So the problem increases and increases, right? And typically you see this, the learning as three main approaches, or three main imitation learning approaches. The first one, as you can see in this very nice picture, this is a Japanese family cleaning the garden. And then you see the younger girl here. She's doing this imitation based on appearance. So she looks at mother and she says, okay, I will do this trajectory. And based on the trajectory, they are similar. But in the sense, the goal is not achieved because she's just sweeping the floor, the leaves from one place to the other, right? Then you look at the middle one, guy here, and then you see, okay, he has a better tool and the trajectory is a little bit better. He obtains better parameters and he learns more movements, better movements, but still the goal is not achieved, right? So the leaves are still being spread all over the garden. And interesting, you see the elder child here. And here he has a completely different tool from the mother, and he has this extra tool to collect the leaves because he understood that the purpose of the day was to clean the garden, and he, based on his experience and based on the extraction of the main goal, was able to achieve the task, right? And that's why this is very important. And I'm focusing on what we call the purposive learning, which is the new trend of explainability AI. And basically we have the demonstrations based from different sensors. Then we have this generalization or semantic representations that we have here is basically the mapping between the signals to some abstract symbolic representation that could be enhanced with an ontology-based system or a graphical representation or grammars, for example. And then we can use this kind of sequence of actions to execute it on the robot. For the execution, then we can have two different paradigms. One is the physical rehearsal. So imagine you learn an activity, and the more you do this activity, the better skilled you are and executed it time after time, right? And this is what we call the physical rehearsal. You physically rehearse and rehearse, or the robot physically rehearse, and then he gets better in obtaining the parameters. And we also have the mental rehearsal. So it's the robot that he is mentally thinking about the steps that he's going to execute. And then he says, okay, so if I execute this with these parameters, maybe I will fail, maybe I'll succeed. And then I'll, instead of trying it, I physically, mentally rehearse, and then I observe if I will succeed or not, right? So these are the challenges that are now in this purposive learning approaches. And what I propose during my PhD and the postdoc idea at TOMM is let's create this architecture or this system, semantic system, that is agnostic to the different input sensor data. Remember, the robots will have different sensors, and that's why we need to think of sensor agnostic. So we can have single videos from YouTube channels, for example. We can have multiple videos where the gaze could also be analyzed. We could have virtual reality or robotic sensors, so you can kinesthetically guide or teach the robot, right? All this information can come to this atomic, what do I call atomic property detector. Basically, this module is the one that is going to extract the information, the trajectories, and is going to map this trajectory to these labels or symbols. And those symbols are going to be used to create semantic rules. So combine the information of the environment plus the information of the hand to represent goal-directed movements, right? And then we have the inference and the knowledge module, which is in this case an ontology that is enhancing the rules that we obtained here. And we can have the task generator module. This is basically the graph representation that we obtain, but we also including the precondition, postcondition, so that we can later on execute it on the robot as a planner, for example, right? And then each of these steps in the planner are going to be created or grounded as a primitive movement for each of the robots. And in this sense, these need to be adapted to each of the robots. So if you see here, this gray module here, or these modules that are the gray area, these are the components that are the semantic representations that we obtain. Whereas, and this is going to be robot agnostic, whereas the green area here is going to be depending on the architecture of the robot, and this need to be adapted and changing to all these different platforms, right? But before we get into details, first we need to define the levels of abstraction. We are talking about this abstraction and semantics, and of course, depends on the level, is the action that you are going to recognize, right? For example, we can have two different spaces. The first one is the execution space. This is the space when robot is obtaining the parameters, adapting the parameters, creating the primitives, defining if he needs to use force or just inverse kinematics or Cartesian control and impedance or whatever. So this will be the primitive of the action lowest level. Then we can have the problem space, and this is a little bit higher representation. And the primitive activities will be, for example, idle or reaching or taking, because this represents the lowest level that we can divide task, let's say. Then tasks are basically the concatenation or the combination of different activities. For example, picking an orange is the composition of idling, reaching the orange, grasping the orange, and this is picking the orange. And then placing the orange is starting from taking, putting, and release, etc. And then if we combine different tasks, then we go higher into the presentation, which is basically the process. In this case, would be sorting fruits, like you can see in this picture here with the lady. She is basically sorting fruits and sorting oranges, and for the lady it's very easy. She doesn't even think about it, but internally I think she's representing these different hierarchies. Okay, so if we assume that we have this hierarchy representation, then we go from the low level to the high level. The low level, basically, if you have images, you will create or videos. You can obtain color blocks, for example, and then you can track the position of the hand, the position of the objects, and the environment. And from these, you can obtain trajectories. Like, for example, here you have the velocity of the hand, right? How fast the hand is moving when you are doing these actions. But you could also have distances, so the distance between the hand and the objects on the environment, so you can interpret how these change. And then, of course, if you segment this signal and you just analyze the signals that belong to the same class, like, for example, here, put something somewhere, is here, observe, and then here again, and then here again, and here again. And then if we just observe these signals, you will see that the amplitude of velocity is different, right? And if we send these signals to a classifier, the classifier most likely is going to tell you, oh, I observe two different amplitudes, so this will be two different classes. And if we do the same for the distance, you can see that there are different trajectories, and then a classifier will be confused that this is not the same action, right? So basically what we do is we combine all these signals with the semantic representation rules that we obtain from these parameters, and then we infer a higher level action. In this case, we see that when we have either of these velocities, it doesn't matter. If, as long as they have this semantic representation, then those are going to be clustered as the same put something somewhere activity. I will explain more detail this. So how do we obtain the semantic rules? So this is basically the core of the whole thing. So the first thing is, of course, we are thinking about abstractions, and the first thing is we need to obtain the most primitive movements and information from the environment that we can transfer towards different sensors, towards different environments. And after a lot of analysis, I find out that if you detect the velocity of the hand and you can cluster them into the hand is moving or not moving, is basically the velocity, and then you just threshold it, and then you can see the hand is moving or not moving, right? For the object acted on, is basically the distance between the end effector and the object. So for example, you have a cup here and the hand is getting closer to the object, so the distance is decreasing, and that would be when the threshold is getting closer, then you acted on the object, and when the object is already very, very close to the hand, then is switching to object in hand. So based on the distance on these two positions. Once we have this segmentation of the environment and the hand information, we use this in training phase, and we use a decision tree system C45 algorithm, the classical one, and we have two steps. The first step is to define the basic activities. So imagine you observe someone cutting the bread. You remember the first video I showed you of the person cutting the bread. We want to detect the basic activities, and then we can have these granular activities. Granular activities mean that you cut or you sprinkle or you pour. These are activities that cannot be generalized as basic activities, right? Then this information can be, the tree that we obtain can be transferred to semantic rules, and these semantic rules can be include an ontology to make it more general. Using this in mind, basically what we do is we obtain this information. This is the semantic rules of the tree that we obtain. So we have the basic activities, which are only 5 here. And it's very easy to demonstrate. So if the robot is here right now, looking at me, he will see that my hand is not moving. So basically this branch here, that I have something in my hand. In this case, something is equal to cup. And this is when the generalization is coming in place. And here's something is going to be, it's a superclass from the ontology that I will show you in the next slide. And then grasping. So now I'm grasping the cup, right? And since it's a semantic extraction, it doesn't matter if you have it on the right hand or the left hand. Semantically, they mean the same, right? However, there are some actions, we call it granular activities. In this case, it's very difficult to make such generalization like something or nothing, because imagine this pen is a knife, right? And if I have a knife in my hand, like here, object in hand equal to knife, that from this information, you don't actually know what I'm going to do with the knife, right? So I could just leave it, or I could just put it in the dishwasher. But if you see that there is a bread here and I'm going to act, the knife is going to act on the bread, then for you it makes sense that the probability that she's going to cut then is higher than she's going to put it on the dishwasher, right? So basically, this is what the system is extracting. So when you have in your hand the knife and the knife is acted on the bread, then you're most likely going to cut. And the interesting part here is we have tested this into so many different data sets that we observe that we are able to create new knowledge on demand. Of course, not all knowledge is correct, but it's a good starting point. And as I said, the semantic rules that we obtain are actually enhanced with an ontology. And in this case, we're using the first order logic to map these if-then rules from the decision tree to the first order logic. And here you see this something is basically calling an ontology. And from the ontology, we can have these two sets of information. We can have the basic knowledge, the knowledge that it's already prior information from the ontology, but we could also get infer knowledge. So this is knowledge the system is learning on demand based on the real instances that is surrounding the environment. This is here, and this infer knowledge is possible due to the observational and semantic rules that we obtain here. So we are creating knowledge on demand, basically. And I will show you a video here. So this is, imagine you are in, the robot is observing a YouTube video, and he observes this is the simplistic color-based system that is in the literature, the color-based, based on the color, the bread, the knife, and the hand. And here you see the system is able to detect cutting, which is correct because this is the data set we use to train the system. So this is not surprise, right? But then we say, okay, can we test that the semantic representation, the rules that we obtain are actually able to use in a different data set? And as you can see here, we have a new data set. This is exactly the same semantic rules. The only thing we change, of course, is the color and the new labels of the object. That's it. And now the system is detecting, okay, you're reaching, now you're grasping, now you're putting something, now you're holding or taking, now you're putting something. And this is interesting. The system, or the learning system, was able to detect, okay, I have this new activity that I have never seen before. It contains, you have in your hand a pancake mix, which is here, and you have your acted on the electric stove here. And then via active learning is asking the user, is this correct? You just say yes, and then you just include the new label of the activity. And as you see, this is being included into the new infer knowledge in your dataset or your ontology. And basically the system now knows how to detect cutting and how to detect pouring, right? But just observing this video. So this was good, interesting result, right? But then the next step is, okay, what happened? Do you remember the video I showed you at the beginning with the 3 persons doing the rolling the bread and the left-handed for cutting? And then we have these 2 different new activities of pouring and flipping. And as a reminder, we only use this demonstration of the person doing the normal cutting for training to extract the semantic rules. And the percentages you can see here on the lower part is basically the percentage of recognizing the activities of both hands at the same time. You notice that there is a lower number here on the left-hand person, and this is because there is a lot of occlusions. We are still using the object, the color-based system, and you see here there is a lot of occlusions that the color system cannot handle. Therefore, this information is noisy to the system. But still, we have a very good, kind of decent number for the recognition of a new system if we consider that we didn't train to get these numbers, right? And of course, we want to have this capability included into a robot. And for this, speed is very important. So we don't want our robot to think for half an hour, make a decision, and then act. No, this needs to be a very fast process. So we have the perception of the video, the extraction of the pictures, the inference of the goal. This goes to the scale planner. The scale planner could be any planner you want, PDDL or sequence planner or ROS plan or whatever planner. Then you have your primitives. In this case, we have predefined primitives like inverse kinematics, marker. And then the robot is going to act, right? So here, this is the video that the robot is just watching. This is the camera of the robot, and this is the inference that the robot is doing. You see this, the speed that the robot is recognizing is very fast. Here, for example, he even detected that pouring was happening even before pouring was finished in the video, right? And then we say, okay, let's make it even more interesting. We have a new robot, which is dual arm, and we have the person. Remember that she was rolling the bread, and since we are extracting semantics, we want the robot not to imitate, because it will be really weird to see the robot twisting the bread, right? And here you see another interesting factor to consider when we do dual arm manipulation is the synchronization. How does the robot know that he first needs to move the bread and then make the cut? Well, actually, this is demonstrated. There is a lot of information that is demonstrated we don't even realize, but it's already here. When you demonstrate, you first move the bread and then you cut, and each participant will do the same. So this information is infer, and then the robot is able to execute the steps. And you saw the robot was not twisting the bread as he saw in the video, but he was executing the primitive that it was optimized for doing the cut, right? And then this is the video I showed you at the beginning from the virtual reality. And in the virtual reality, we just told the participants, this is the environment, you are in a new kitchen, can you just do the dishes? And the system is able to detect each of the actions the person is doing. Like you can see here, we have the segmentation, and then we have what we call the task graph. This is kind of how the system is creating the sequence of actions that is being detected and the concatenation of them. And for this, we asked 11 participants, and we didn't give any specific about the task. We just told them, do the dishes. Some people cleaned the kitchen, some people did more than doing the dishes. And that, of course, generated different task graphs. But we observed that if we combine all these task graphs into a single one, we can see clearly that there are some certain nodes that are visited most of the time. So based on the frequency that these connections were made from the demonstrations, we can actually use these most frequent ones to actually command the robot to do those sequence, right? And of course, in this case, the robot is using both resources, so both arms at the same time. And here you see the robot is choosing to get the sponge from the right gripper because it's closer, and this because it's closer, not because he observed that from the video, because from the video you don't really have this information, or we don't save this information from. This is a collaboration we have with Japan. And yes, so these are basically the videos I just show you. And then how can we extend this to include new sensors? Now imagine you don't want to teach robots via videos or via virtual reality. You have a robot and you want that people kinesthetically teach something to the robot. So basically it's the only thing you need to change is how to encode this information into this atomic property detector module that I described before to get the symbols that you need, and the rest is exactly the same, thanks to the semantics that we obtain. So in this video, I'll show you, this is the outcome of our EU project, the Factory in a Day project. Here, the operator is basically just moving the robot. This, you can see here, is the recognition that the robot is automatically doing. what you can see here on the upper part here is the recognition. Here you can see the observations that he's doing with his camera. And we have the tactile sensor here, and the robot is detecting how stiff or how hard the orange is. And based on that, you can see this is the recognition that system is doing, and not everything is correct, as I said, and it's the job of the operator to say, remove this from the sequence. And here the operator is teaching, okay, this is a good orange, you need to put it on the correct box, right? So if it's a good orange, you just put it here. If it's a bad orange, you just put it to the trash, because we're going to make juice to this orange, right? And then, okay, so this is the demonstration. What happens in the execution? So in the execution, basically, we can have different tasks, so similar to the task graph that we showed before. But here, we're extracting precondition, postcondition for the task. And based on this, these tasks are basically kind of concatenated. This information is like a template, and is going to be instantiated. So you can see here is this orange when the perception is happening. So in this first demonstration here, you see that the robot now has two end effectors that are able to work together, and he basically uses both hands at the same time. And for the oranges, that he knows what to do. But now he has apples here. What is he supposed to do with apples? And then here we have the errors. So based on the inference here, the oranges, this is not a problem. He knows what to do with this. With the apples, interestingly, by itself, here DEC recognizes that apples doesn't have the property of squishability, because this is something that we already included in the ontology, that apples should not be squished. But the inference detects that he should not do some steps and directly go to packing. And here, the last video shows the error recovery. So the operator is basically disturbing the robot. And when the robot is executing task 2, let's say, there is a failure here. And the robot detects this error, and he's trying to recover him from the error. He fails again, and he tries again until he succeeds, right? So this is interesting. So these gray areas are the actions the robot by itself decide not to execute when there is an apple present. And when there is an error, for example, here, he can look based on the preconditions, which is the next task he needs to do and execute to recover. And then, since now due to the corona, we are working mostly for home, we have a lot of simulation-based system. An interesting thing is, okay, how can we transfer this kinesthetic teaching that we normally do in the lab into these virtual scenarios? Is it possible? Can we have the similar information? And this is a study that we are doing in collaboration with our Japanese partners here. You see, the operator could be in Japan and the robot could be in Germany or in Sweden, and it doesn't matter. You are both into the virtual environment. And what we did in this analysis is we check if the trajectory that we obtain from the real kinesthetic teaching could be used in the simulation and vice versa. The information that we use from the virtual reality can we actually use to manipulate the real robot. So basically sim to real transfer. And what we find out is actually it's quite close. It's not perfect, of course, but it's close. So we could potentially use this information for a training system. So especially when we need a very expensive system like reinforcement learning that you need lots of training, this could be one alternative. Then the next thing is, okay, we have this nice system which demonstrates, you learn the steps, but how do you check that these steps are correct? How do you check that the execution the robot is going to do is going to be correct? And for that, we have my student Maxi has designed a system that is using augmented reality to show the operator what are the steps the robot has detected to do, has planned to do, and how is going to be the movement before the robots do it into this augmented reality. If the operator is okay with that movement, then he goes and say, okay, go ahead, execute this movement. I'm confident that you're not going to smash my China silverware or something like that. And this is a study that we did with the augmented reality. So on the first part here, you can see this is the HoloLens visualization. The one in the middle is a tablet with augmented reality. And the last one here is a classical visualization tool for robotics, which is REEM-C. And this is a very minimalistic one, so you are not embedded in the scenario. And we find out that, first, users don't recognize errors when the robot collides with himself, for example. This is something because inexpert users don't know where to look. For example, they fixate on the end effector and they forget about the other joints. This was very interesting finding for us. But they know that on the other hand, they're able to detect when the sequence is not correct because it doesn't really make sense to them before the robot executes something. So this was a very interesting result that we had, and Maxi presented at Roman last year. And this year we submitted a paper in IROS. Let's see, the community thinks. Basically, the demonstrations you have from the virtual reality, and then you have the segmentation, but from the segmentation, you want to create the operators. What is the information that the robot will need in an operator for a planner? So for PDDL, for example, you need this operator generator, the domain, and then you need a lot of information. Which is typically hand-coded when an expert has all this information. So in this case, we use the information that we obtained from the demonstrations and from the recognition of actions. And the system was detecting, okay, this is a precondition, this is a post-condition, and this is information from the environment change, this is information from the execution change or so. And based on this, we were able to send this to a planner, PDDL. PDDL was able to detect the steps, and we were able to tell, okay, is this an executable plan or not? And of course, the interesting part here is we are generalizing in a sense that the system is able to create plans even for tasks that he has not seen before. In all the demonstrations, the participants were only stacking 2 cubes, either with the right hand or with the left hand. And you can see here in this segmentation that we can see different variations from demonstration 1 to demonstration 2. And when we tested, we see this goal 3 and 4, those were never demonstrated, and still the system was able to actually correctly detect the demonstrations, right? So here we see the video, very interesting. This participant here on the second one is hesitant on grasping, and you see that segmentation is completely different from participant to participant. And it's interesting because then the operator, the planner of our system needs to get as many operators automatically as possible to actually create the plan, the PDL plan, the domain, all this information needed for the execution. And then here we tell the robot, okay, you're going to execute this goal. And surprisingly for us, the robot was executing, for example, here you see in this video, he's stacking 1 cube on top of the other. So he's doing the upper part of the goal. And then he's grasping 2 cubes at the same time and putting it on top of the other one. And this was not demonstrated. So we were very fascinated with these results. And then, yes. So we also have this Mensa simulation. So we still have collaboration with TOMM. And in this case, we have obtained this causal relationship between actions and environment. For example, here, it's important that first, when you're setting the table, first you open this drawer door, and then you take out the dish, otherwise you're going to smash the glass window, right? So these sequences were automatically obtained from these virtual demonstrations as well. This was presented at IROS last year. And this year we are basically starting this new project, CRAFT, this collaborative assistant for technicians. This is funded by CHAIR, this is the Chalmers AI initiative. And here basically we want to deal with human-robot collaboration. So especially here, which are the roles that robot needs to take to help humans, like here changing the wheels and difficult interesting problems, including human in the loop, etc. So yeah, so just to summarize and finish, because I think I'm running out of time. The main things I'm investigating is basically how to segment, how to recognize human activities online, because we need these systems to happen online. It needs to be flexible and adaptable to all these different situations, because exceptions happen all the time. The knowledge that we need to obtain needs to be transferable to different domains, like I was showing, from making a sandwich to making a pancake to storing oranges, and needs to scale. So he needs to learn new things on demand. And the question is, how do we know this is actually good or bad? So these are things I'm still investigating. Of course, I want to thank all collaborators and research fundings, of course. And that's it. That will be the end of my presentation. Thank you very much.